Okay, so we'll make a start. Good morning, everybody. I'm Michael Crawford. I'm CEO of the Source ARC. Welcome to the next episode of our fortnightly webinar series. Today we're hearing from Professor Chen of Griffith University on evaluating alternative rhizobial carriers for improving soil performance. But just before I go there, recognising that we have a very wide, broad and diverse audience, and there'll be some people there who perhaps are not familiar with the Source ARC. A few words. Essentially, the Source ARC is a virtual research centre, a collaboration of 40 organisations across Australia and New Zealand, including 8 universities, 4 state government agencies, a range of industry partners, and importantly, 20 grower groups. We have funding, both cash and in kind, from our partners and from the Commonwealth Government, the Australian Government. And our purpose is to undertake R&D to give farmers the tools and knowledge they need to improve their soil performance, their soil management, and ultimately their productivity and profitability. This seminar today is part of a regular series we have now. And just looking ahead, in 2 weeks' time, we have a webinar on developing an e-nose or electronic nose for smelling soil. And so a new piece of technology that's been developed to help measure the soil biological activity. 2 weeks after that, importantly note, on a Thursday, not a Tuesday, we have a seminar on improving decision support systems, how we can get greater functionality around soil dynamic processes into models like APSIM, etc. And then 2 weeks after that, in September, 22nd September, a seminar looking at some social research, adoption research on caring for the land, farm care networks, and adoptability of soil improvement techniques and practices. Why do farmers do what they do, or don't do what they do, what they don't do? All those webinars can be registered for via our website, much the same process as which you registered for this webinar today. So you can go to our website, or you can, and in turn, you can please follow us on Twitter, LinkedIn, or via our YouTube channel as well. So today's webinar is being recorded. We will therefore be able to make it available for you to view afterwards at a later date via our website, or for your colleagues who aren't here today, they can also view it via the website. The way the webinar will work, I'll shortly introduce Chen. He'll give a talk for 20 to 25 minutes, and then we'll have a period for questions at the end. The way the questions work is, please type your questions into the Q&A box, and we'll be able to read the questions from the Q&A box. There's also a chat box. You can use that for comments, for chats, etc. But questions, do that via the Q&A box. And I'll read them out at the end, and Chen will be able to answer them. So, to introduce Chen, Professor Chenron Chen is a professor of biogeochemistry in the School of Environment and Science at Griffith University in Brisbane, Queensland. He leads a team there investigating environmental aspects of soil performance and related issues, bringing a whole lot of skills, but focused around biogeochemistry. He's a key researcher in the Source ARC with him and his colleagues there. Today's talk is on a project that he leads, and today's talk is entitled Evaluating Alternative Rhizobial Carriers for Improving Soil Performance. So I'll stop sharing and I'll introduce Chen.
Thank you, Michael, for your introduction. And good morning, everybody. And thank you so much for attending this talk. My name is Chen, and I'm a professor in environmental biogeochemistry at Griffith University, and currently is a leader of this research group and the 4R Waste Hub at Griffith University. Today, I'm going to talk about is developing the alternative microbial carrier for lower formation, the rhizobium formulation to improve soil productivity. I'm going to share the screen now. Can you guys see my
Yes,
screen?
very good, Chen. We can see that clearly. Thank you.
Thank you. Before I forget, I'd like to acknowledge this support and contribution from the project, the research partners and the industry partner for their support and patience in the past nearly 2 years now. We also have some these partners and the industry partners from outside the CRC, for example, Green Loop and the Glassdale and other these animals and the also, I'd like to acknowledge this the support from Australia Inoculant Research Group. It provides three these major strengths of rhizobium for this research. In terms of research staff members and students and the associate with this project, currently we have one postdoc, the Dr. Yantao Li, is in material science, and working on this project since May 2019. We have PhD student Rahab Cosme and study October 2019, and they both there has been doing very well for this project. Anita worked for this project for 5 months and left September 2019. This research topic is very classical, it's an older topic, and we know a lot about this, the rhizobium, bacteria, nitrogen fixation, and symbiosis. Overall, rhizobium, the bacteria, play a very important role in the farming activity, providing about 100 kilogram nitrogen per hectare per year. It's about 1/3 of this nitrogen requirement for the leguminous plants. The current rhizobium, the inoculants, and the rhizobium strength and the rhizobium bacteria, the survival rate is quite low, and is unseed coating because of this desiccation and heat, and also the availability of this peat. Currently, this about 70% is peat used in Australia are imported from overseas. The quality is not it's another issues. So all these material, these issues are limited. The potentials of rhizobium inoculants that use. For CRC project, we were aiming to evaluate alternative microbial carriers to improve this soil performance. In terms of selecting the alternative materials, we are aiming this the locally available, affordable materials, which a farmer can use easily. So we focus on these locally, the organic, inorganic clay materials and the biopolymers. They are locally available, they're cheap, affordable, farmer can use. But also the other area, nanomaterial, could potentially and the very effective in delivering this rhizobium bacteria, but they may be expensive. We also have done some work on this, but our focus is on the locally available organic, inorganic material. So this material have to be able to facilitate loading the bacteria, support the growth of the rhizobium bacteria. Also, it's good for soil and plants, with optimum physical, chemical properties, and also have to be cost effective and without toxicity to the environment. So far, we have collected over 100 types of materials and could be potentially used as rhizobium carriers. These materials come from including these the soil, minerals, peat, these clays, plant waste, biopolymers. Also, these materials sometimes when they come from a commercial company, different cow manure compost, recycled rockwood, polyacrylamide, and some materials are created in our lab, and for some of biochars we produce from different feedstocks under different pyrolysis temperature, and also some biopolymers produced in our lab. These slides show the facilities we use to produce different biochars, including these tile biochars here. These tile biochars. And then this is cow manures we use from we got from this Glassdale and using this study. These are the key facilities for characterizing these functional materials: SEM, this FTIR, and the pressure membranes we use to measure water retention curve. Also, we have this 400, 300 these megahertz on the nuclear magnetic resonance spectral meters we can use to characterize this and the chemical compositions of these materials. Here are some results and for the chemical properties of these alternative materials. We measure these the key elements: carbon, nitrogen, hydrogen, oxygen, phosphorus, and sulfur. These are key elements and important for the strain survival. And also we measure this the soil pH, microelements, which also may be important for this rhizobial strain growth and the survival. The materials with neutral environments, such as cow manure, biochars from the alocasuarina, pine wood, hay, mule mud, they are enriched in the above mentioned elements and may have this better performance as a rhizobian carriers. This is just from the chemical properties perspective. So now we look at this surface structure. We use SEM, scanning electron microscope, to look at the surface of these materials. For example, some biochars is, they produce at the very high temperatures. You cannot see much of these polars or fibers or these channel structures. It's like lump, and surface, the area is low. And some material diatomite and with porous structure, you can see the hole. And the fiber-like structure, and they from recycled wood, and channel structures, and for biochar produced at a low temperature, 400 degrees. From this SEM and BED surface area, the measurements and the material with channel and porous or fiber-like structure normally can provide best habitats for rhizobian bacteria. This material includes then this, this biochar from alocasuarina and pine wood, and diatomite, and perlite, and some material this with a fiber-like structure, like recycled rock wood. So this material have the better potential and to be used as rhizobian carrier materials. So biochar with large BET surface area, and could be better than those with a lower surface area. Normally, there's a lower temperature biochar, there is better than the higher temperature biochar in this surface area. We also they determine it's a functional group using FTIR. And the cow manure, you can see cow manure has quite a few these functional groups here. Okay, there's amine, alkyl, and hydroxyl group. But compared with sand, it's the only group functional group we can say this is alkyl. Okay. From the analysis we have done, and the materials with functional groups such as this amine, hydroxyl, carboxyl, and alkyl are beneficial water retention and attachment and survival of rhizobian bacteria. Bacteria including this cow manure, diatomite, mule mud, hay, cellulose. They are rich in various functional groups. They present this better potential as a rhizobian carriers. This is from the perspective of functional group of this material. In terms of the water retaining capacities, we use pressure membrane to measure water retention curve of different materials. So we can see in this from this graph here, the water retention, the water contents, the y-axis is water content, and the x-axis is the pressures we apply. Okay, so we can see in this some material, for example, diatomite, that still can retain the 80, the 50 to 80% of this water. Okay, when we apply higher pressure, like 10, 12, 10, 14 bars. Okay, some other material can only retain this 35 to 45%, and some then 10 to 25%. The lowest one we 5 to 15%. So there are big variations in water retaining capacities among this material we are testing. So there are some potentially these very useful materials with good water retention capacity. For example, this peanut shell, this diatomite sugarcane, alocationina, and they have quite, quite good this water holding capacity, and what some other material, for example, biochars and the pine wood materials have low water holding capacity. The other characteristic we measure is water releasing properties, because this is critical in this maintaining water supply for a longer time for rhizobium to survive, rhizobium bacteria to survive. So from the material we testing, and the majority of material lost water quite quickly within the 1 day. And there are some other material that can keep this moisture for a longer time. This material, including this polyacrylamide, recycled rockwood, diatomite, and cow manures. They actually have slow release, slow water release characteristic. So this material had a better potential to be used as a rhizobium carrier. This water releasing the characteristic is measured at 30 degrees. So water actually under this heat, and water evaporate and slowly and over time. This is the microbiological lab in our university, and we use for this research. And but we also have this very good the modern molecular microbiology lab, and involved in DNA research, and could potentially use for this research. Here are the three major strains on the CB1809 and CC1192 and the RR1 and RRI128. These three major strains used for the soybean, chickpea, and luzerne, and we get from Australia Inoculants Research Group for this research. I'm not going to go through these details of the protocol. We all follow these standard protocols, and for the culture incubation and inoculation, we just follow the standard protocol. So from the material we are testing, and we determine this colony forming unit value, and using this and the dilution plating methods, very classical method as day 20, 40, 60s after incubation. We measure survival rate and share life. So here are some results. These figures show this colony, the forming unit value of inoculants with different types of carriers materials at 28 degrees at day 20, 40, and 60. We have control here, and we have control here. It's imported peat, okay, and also we have Australia peat as a control. So from this diagram, we can see there are some materials are better than the others, okay? And the most carrier materials are better than imported peat. and in CFU value at the different days. Some materials like plant waste, animal waste, and cow manures, and such as diatomite, muriate, and the cow manure and chicken manure are better than or comparable to Australia peat in CFU value. This is materials here in the middle. We also have tested some biochar materials and which produce at a different temperature and pyrolysis temperatures. We look at the result here. We also use this imported peat and Australia peat as a control. Okay, so this most biochar carrier materials are better than imported peat. You can see this most biochar material is better than this imported peat, and in the CFU and biochar material produced at a lower temperature and 400 degrees is better or comparable to Australia peat in CFU. So it seems that the biochar produced at a lower temperature had this better potential to be used as rhizobial carrier. To conclude, and there are several locally available materials, including these minerals, plant waste, and cow manures, and biochar materials produced at a lower pyrolysis temperature at a better structural properties. So this this material and they normally have this the large functional group, and they demonstrating greater water retaining capacity, are better habitats for rhizobium bacteria. Rhizobium strains and CB1809 showed a better survival rate and longer shelf life in the above materials than or comparable to peat materials. And the control we use, they can maintain the highest the CFU value and for a longer time, indicate great potential as alternative career to peat. So the ongoing the experimental work, including this optimized this inoculant formulation, we're going to find this the best recipes and to combine some of these best materials. And we also we need to assess the survival rate under drought and other stress. And we need to set up this port trial to look at this survival rate, modulation, nitrogen release activity, nitrogen fixation rate, and we need to evaluate environmental toxicities. In terms of future research, we will continue to search for the locally available low-cost alternative materials. And also, this new formulation of inoculants based on the alternative will be developed. And we will continue to test these properties. And port trial and field trial experiment will be carried out to assess this, impact of this bioformulation on nitrogen fixation on plant growth at different soil type and the different ecological condition. We will need to establish the collaborations with commercial partners for effective improvement and the production of this alternative novel inoculants. Thank you so much for your attention. And if you have any question, and I'm happy to answer now. And if I'm not able to answer your question right now, please email me. My email is c.chen@griffiths.edu.au. Thank you so much.
Thank you very much, Chen, for that overview of the research that you have been doing with your team, looking at evaluating potential alternative microbial carriers to peat. So yes, everyone, we've got the opportunity to ask questions now. There's already a few questions in the Q&A box. Chen, if you can stop sharing your screen.
Yeah.
And then your videos will come up.
Yeah, okay. Question.
So that's it. Yeah, type questions into the Q&A box. And if there's a question there that you particularly like, you can upvote it by clicking on the thumbs up sign, I think, and I'll go to the top of the list and get priority. But Chen, if I can start with the first question here from Daniel, in relation to water retention, have you tested the water retention of peat, which is the most common used carrier in the market?
Yes, we did some analysis. I'm not sure the data is here. The peat actually quite good in moisture retention. Let me find out if I have some data here. It's a very good question. We'll see how this peat. I'm sure we have done the peak, but there's no data here. The peak had quite good moisture retention, but the still not good enough in this formulation to maintain this moisture supply. Otherwise, the desiccation won't be an issue for survival rate.
Okay, thanks, Chen. When you find your data, you might like to follow up with Daniel directly.
Yeah, thank you, Daniel. It's a very good question. Sorry.
From Susu Win, and I think Susu's in Myanmar. We do have a couple of people looking for these webinars internationally, so welcome. For media for rhizobia, peat is the best one. Can we use charcoal rice husk instead of peat?
That's a very good question. Peat is being used and as main this matrix, to carry this main material to carry this rhizobium and the bacteria. The problem with peat, as I mentioned before, although peat can retain quite a lot of moisture, but they cannot supply this water in the long term, and at least a month. And the other thing, peat in terms is non-renewable resource. Okay, and currently in Australia we use the peat. Most peat actually imported from the other countries. Charcoal is got a potential, and that could be used for the as a rhizobium, the carrier. The charcoal has some similar properties to biochars, and could be tested. But I think from all this material we characterize, I think not a single material has this combination of these best properties, best chemical properties, both best surface properties, together. So we need to find out this optimum recipes to combine these key materials, and for the as a rhizobium, the carrier.
Thank you. So from Aravind, have you measured heavy metals in your 100 various materials?
We have done, not all, at least we already done the ICP and analysis, and the majority of this material, the heavy metal, they are not very high, okay, they are okay. And including this cow manure, they are not very high, but we need to, it's a good question, that's why we need to do environmental, risk and the toxicity and evaluation.
And I think the other factor is at the rate at which the carrier would be used in the field will also be very low. So it'd be a very minute amount that would be applied. Next question is from Lucas. Have you looked at leaching the alkalinity from the biochars via activation of phosphoric acid, etc.? This increases the functionality and potentially a more pH neutral environment for the rhizobia.
Very good question. Thank you so much, Lucas. For biochar, we use this for testing. I don't think we have done this acid wash, and we did it before for other project, to wash this ash out. And but we can test and can do it again to look into this. It's a very good suggestion. Thank you, Lucas.
From Aravind, Chen, how will farmers benefit from the project outcomes?
I think there's two perspectives. if we increase this, if we can come out this commercially viable and the rhizobial formulation, farmer they will have this better product and they with the higher survival rate, and they will use a small quantity, and they also this the cheaper. Number one. Secondly, this material, if we find now some this locally available, affordable these materials, farmer can use to make their own inoculants. Okay. I'm
Thank
sure
you.
that the farmer will benefit from this this project.
Thank you, Chen. And I'll add to that also. Yeah, from a farmer perspective, yeah, mixing up peat inoculant, coating seed in a shed on a cold night in May, when you're trying to get your harvest, your sowing operation done, it's messy, it's sloppy. If there's alternatives to having to work with peat slurries, that will also bring joy to many farmers, as well as increasing the effectiveness of the rhizobial inoculation. A technical question about the water retention results. Were they gravimetric or volumetric?
It's a gravimetric.
Okay, short and sharp. In the mineral carriers, did you say that zeolite was the best carrier?
The zeolite is not the best carrier, and the zeolite got a potential. Okay, we can use as the microbial carrier. The problem, we have done over 100 materials. The problem is none of these individual material that has all these best chemical, structural, physical properties. Okay, we need eventually we need to combine this material and they make this to optimize these recipes to produce this the best inoculant.
There's a question there from Nancy. Are you thinking of making an economic evaluation of alternative products in comparison to the commonly used peat medium?
It's a very good question from Nancy. Thank you. Economic and viability is critical for the potential commercialization of this novel and rhizobium formulation. We are doing this economic and analysis at the later stages, and currently most of these materials actually come from so-called recycle or waste. Okay, and to me now economic economic may not be the key issues, but we do need to do the economic evaluation at the later stages, and in comparison with the peat currently used for this rhizobium industry.
Thanks, Chen. And as CEO of Assor CRC, I'll add to that the general comment. In all our research, as our R&D generates information around potential products for future development, we take it both to a higher technological readiness level and a higher commercial readiness level. And as we progress through those various commercial readiness levels, we'll be working with partners, potentially with commercial partners, to assess and evaluate that business case, the commercial feasibility, viability of taking these products through to market. First, we've got to look at the science to just assess where the scientific opportunity is. So moving on, yeah, it's probably a similar question from Brad, that Australian peat used by the inoculant industry costs about 5 cents a kilogram. What are the estimated costs for the alternatives?
This is the economic analysis we need to do, and the other thing, we, as I mentioned before, peat is cheap. I understand is cheap at the moment, and but 70%, about 26,000 tons are imported every year from overseas, and if we look at this availability of the resources, and peat is not renewable, and eventually we'll run out.
Thank you. Jen, did you study other stress rather than water stress in peat, and mainly in relation to long-term survival of rhizobia? Did you find any physiological effects? Which solution is best for nutrient-limited conditions?
That's a very good question. Yeah, initially we wanted to focus on the drought and the desiccations and the stress on the rhizobian survival. I think that we need to explore and a little bit broader. And in terms of stress, for example, is acidity and salinity stress. Then also, to me, in the past few months, we feel these materials. It's not only the structure and the all functional group that are important for the best habitat of this rhizobian bacteria. And some, for example, this carbon, we find the carbon availability, all these microbial nutrients, and maybe some other, the chemicals are critical for the growth and survival of these rhizobian bacteria on these materials. We need to look into that. Thank you.
Okay. Jen, how would a crop residue biochar with a higher nutrient, nitrogen, potassium content fare as a carrier?
Let me find out the I think that's good to me. There is good potential and the crop residue biochar with high nutrients. But we need looking into this the other properties as well. The structure and the functional group as well. That's why I mentioned before that we already done this testing of these over 100 materials, and none of the individual this material had all these best and aspect of this, these or best properties for the rhizobian carrier. We need to combine all this this material.
How long does it take to dry the rhizobial coated materials?
This probably take a few. This is a good question actually, and take a few days. Eventually, I need to find out exact date. Okay.
Okay, thank you. Coming to an end. Need to get, or do we need to get EPA or regulatory approval to use waste streams as microbial carriers?
Sorry, which question?
Yeah, this from Aravind.
Okay.
Do we need to get EPA regulatory approval to use waste streams as microbial carriers?
In Queensland, I don't think so. And we have the industry partners in Toowoomba, and they already approached by this rhizobium, the microbial industry, and they want to use their cow, the manure compost as a microbial carrier. They are very interested in that, but I don't think they need the EPA approval in Queensland.
Yeah. Okay.
In New South Wales, and it may be different story. We need to find out.
Yes. Why is peat used now? Is there likely to be resistance to using other material when peat is the norm? Yeah, sorry, Tim, did you hear that?
Yeah. I think the peat, initially, I think peat is a good material. Okay, effectively it's good material, and also I think at the beginning is availability, accessible, and that's why I think the industry use this material, and also this from originally technology we developed, and for inoculants we use peat. The thing, the quantity. Sorry, Michael, is that there? Have I answered this question?
Yeah, I think so. I might have moved it on. Yes, yeah. And Brad's comment is probably related to that, looking at alternatives as well, and some suggestions there. I'll come to the last question from Joe there. You talked about Australian peat and you talked about imported peat. What are the main differences between Australian peat and imported peat?
I think this is a good question. I think that there are some you know the chemical composition. I think there are some difference. Let me find out. In terms of this structure, we should have some data here. But I didn't prepare here today. To me now, the chemical composition that should be there's some difference because they come from different source.
Okay. And Brad's also made the comment to potentially to look at shelf life beyond 80 days, and the current standards puts a shelf life of many strains out to 12 months. Are you looking beyond 60 days?
That's a very good question. Then that's why we need to do more testing. Okay.
Yeah, over longer
period. We understand that.
Jen, if I can finish with a question, but most of the focus here has been on rhizobial inoculants. Increasingly, there's interest in a whole range of other microbial inoculants, both bacterial and fungal, for soil and plant enhancement processes. Is this technology potentially applicable to other microbial inoculants?
Thank you, Michael. This is another very good question. You know, this technology and some of this material will be very useful and as like these microbial carrier materials for other, you know, the fungi and the other organisms. There are some company and they approach us and they try to, you know, to develop some collaboration in terms of these potential the carriers for the other organisms. We are looking into that space as well.
Okay, we'll bring it to an end there. We're just about on 11:45. I thank you, Chen, for your presentation and for answering the questions as you have. And I think the questions both help to clarify the issues of uncertainty, but also help to set and inform future research directions as well. And so we're quite valuable for the team. I think I've just been able to post the slide again with our contact details around the source ARC. Yes, so if you haven't already, please go there, subscribe to our updates and newsletters, follow us on Twitter, connect with us on LinkedIn, subscribe to the YouTube channel, and stay in touch with this and other aspects of research coming out of the soil CRC. So thank you everybody for attending. Thanks again to Chen and his team for the presentation.
Thank you. Bye.